final talk of the first day of our conference. Bjorn Poonen will be speaking to us today about tetrahedra and exponential diophantine equations.
Okay, thank you very much for inviting me. I'm very honored to speak at this conference, at this workshop in honor of Udi. So, all right, so I'm going to talk about several things, and much of it is joint work with Kiran Kedlaya, Alexander Kolpakov, and Michael Rubenstein. And I'm also going to talk about some subsequent work of some undergraduates here at MIT, Anas Chentuf and Yihang Sun. All right, so I'm going to be talking about tetrahedra, and there's some old problems about tetrahedra, many of which are still unsolved. And so one of them dates back essentially to Aristotle, and that's the question about which tetrahedra can tile space. I'm not just talking about regular tetrahedra, I'm talking about any shape. So the question is, which shapes of tetrahedra can tile space? In other words, if you have infinitely many congruent copies of that tetrahedron, can you place them in space so that they're not overlapping only on the boundaries, and their union is the whole space? A second question, which is actually Hilbert's third problem. So Hilbert asked whether you could, which tetrahedra are scissors congruent to a cube, which means, well, scissors congruent to a cube means that you can slice the tetrahedra into pieces with planar slices, with planar cuts, and then reassemble the pieces back into a cube. And he was interested in this because it was part. I mean, the question was whether you could define volume of three-dimensional polytopes, polyhedra, in just by using scissors congruence, whether you could define what it meant for two polyhedra to have the same volume. And so it's something in the foundations of geometry. Okay, so that's Hilbert's third problem. And another problem which could have been asked much earlier, but I guess was asked more recently. So John Conway and Antonia Jones, they asked, can you list all the can you describe all the tetrahedra such that all 6 of the dihedral angles are rational multiples of pi? So yeah, so as you know, dihedral angle of course is just the angle formed by any two faces. All right, so let me start by talking about the second of these, so Hilbert's third problem, about scissors congruence. And so this was solved actually by Hilbert's former student Dane. Actually, it was solved almost before he had a chance to state his problem. In fact, I guess Dane saw a preprint of the list of problems and solved the problem before Hilbert actually gave his lecture. So anyway, and what Dane observed is that there's another invariant besides volume that's preserved under cutting. So I think probably many of you know this story, but anyway, here it is. It's if you have any polyhedron, you can form the following sum where you take the length of each edge tensored with the dihedral angle along that edge, and you view that as an element of this tensor product of Q vector spaces. So real numbers tensored with this quotient Q vector space. Yeah, so the angles are viewed sort of modulo multiples of pi. Yeah, and then the sum of those, if you sum this over all the edges, that's invariant, and it's quite easy to see that this is invariant under slicing, because when you slice each edge, well, I mean, what can happen? I mean, you might slice an edge in two, and in that case, the lengths will be subdivided, but the two pieces will have the same dihedral angle. Or you might slice through an edge, and in that case, the length stays the same, but the dihedral angle gets subdivided, and so on and so on. So yeah, so it's quite easy to see this is an invariant, and yeah, and Dane observed that for the tetrahedron, the regular tetrahedron, and the cube have different invariants. So for the cube it's 0, and so for the tetrahedron it's not 0. But so that already proved that a regular tetrahedron could not be sliced and reassembled into a cube. And in fact, there's an even better theorem. Well, maybe not better, but there's a converse that says that the volume and Dane invariant are the only invariants that you need to decide whether two polyhedra are scissors congruent. So yeah, so that's a converse. Okay, so yeah, so once you know this, then figuring out which tetrahedra is scissors congruent to a cube, you might say, okay, it's a solved problem now. They're exactly the tetrahedra of Dane invariant 0. But I mean, I would like to know more. I mean, can you actually describe what all these I mean, we can calculate the Dane invariant of any given tetrahedron, but can you describe all the ones that have Dane invariant 0? In particular, can you, for example, do they fall into finitely many parameterized families? I mean, is it something like what happens in, say, Mordell-Lang conjecture, where if you intersect, yes, you have some kind of, you have some good behavior of these things. So, and there are some. I'll show you some examples later of these tetrahedra. I mean, they do exist, and there are also some infinite families. But and the infinite families are where the parameters of the tetrahedron variance depend on some parameter. And so yeah, so you could ask, can you list all these families? I don't know the answer to these questions. I mean, we don't know. Part of the problem is to try to find a framework or some kind of general theorem that maybe that would give you some kind of finiteness statement, but it doesn't seem to follow from any of the standard ones that I know of. So I was hoping maybe, I don't know, maybe somebody in the audience can say more. All right, so let me talk a little bit about this problem about well, actually going back to all three problems, and they're actually related. Well, one of the relations is kind of clear. If you have a tetrahedron with rational dihedral angles, then, well, going back to the definition of the Dane invariant, that means that if these angles are rational multiples of pi, then these are all 0 in this quotient group. So the whole Dane invariant will be 0 if all the angles are that way. So yeah, so it's clear that if you have a tetrahedron with rational dihedral angles, then it will be scissors congruent to a cube. What's less obvious is that if you have a tetrahedron that tiles space, then it also must have Dane invariant 0 and also must be scissors congruent to a cube. So this was proved only in 1980 by De Brunner. Okay, so actually, if you're most interested in this tiling problem, if you like ancient problems that essentially go back to Aristotle, but you can view this problem. I mean, even if you're not interested in it for its own right, you can think of this as being like a stepping stone to try to figure out which ones tile R, because maybe you can describe all the families of these and then look within those families to figure out which ones can tile. All right, so maybe I'll go through a little bit of history of these problems. So Aristotle, he claimed that the regular tetrahedron could tile could tile space. Yeah, but okay, and then and I guess when Aristotle says something, people tend to believe him. In fact, in this case, people believed him for about 1800 years. And then after 1800 years, Miller found that this was not correct. Yeah, and then a few centuries later, Hill actually found some other tetrahedra, not regular, that actually did tile. Yeah, so and there's also some one parameter families of tetrahedra, all of which tile. So, okay, and then let's see. So, okay, Dane then invented the Dane invariant. He placed the regular tetrahedron where it belongs in this picture. So yeah, each point here represents one tetrahedron, one shape of tetrahedron. So yeah, it's none of these because Dane invariant is not 0. Okay, Somerville came up with another one that tiles our cube, and those, as far as tiling space, that's the state of these are all that are known. No new one has been found in the last 98 years. On the other hand, in this period, a lot of other examples of Dane invariant 0 tetrahedra were found, and then I started working on this in around 1995, and with Michael Rubenstein, we found a lot of other examples, and then we joined with 2 other people, and we actually proved that at least this list is complete, the one of rational dihedral angles, and we also found some new other infinite families here. Yeah, and the undergrads I mentioned on my first slide, they also found some new examples of Dane invariant zero tetrahedra. So they're actually even more of these little one parameter squiggles here. Okay, so this is sort of where things stand. Actually, I don't quite know if this picture is completely accurate because I haven't actually tested whether all of these fail to tile. I think probably most of them fail to tile, but and actually I think for about 2/3 of them, the undergrads have proved that they don't tile. But okay, anyway, all right. So this is okay. So let me now say a little bit about these problems. So here's what we here's the classification explicitly that I gave here of these rational dihedral angle tetrahedra, the ones for which all 6 dihedral angles are rational multiples of pi. So there are 2 infinite families depending on this parameter x, and so and x should be some rational multiple of pi in this range, and then these are the dihedral angles. So I mean that describes the shape of the tetrahedra. Okay, and then there's a second family. And then in addition to those 2 one-parameter families, there are 59 isolated examples. And well, I mean, we don't quite have good explanations for all of them, but most of them can be explained. Most of them are related to some, well, they're related to some Platonic solids, and you can describe them in various ways in there. There are 2 that are not, well, sorry, there are a few that are not like that. Particularly this first one, I don't really understand why this thing exists, but well, I guess it does. So anyway, we proved that these are the only, these are the only ones. So maybe I want to say a little bit about how you actually prove a theorem like this. So the point is that if you look at the 6 dihedral angles of a tetrahedron, they're constrained by an equation, because I mean the moduli space of the similarity classes is only 5-dimensional, because I mean you can describe a tetrahedron by giving the 6 edge lengths, but then up to scalar they have the same angle. So there's really only a 5-dimensional space. So there must be some equation that relates them, and you can easily write down what that equation is, and it's some algebraic relation, some polynomial relation among the cosines of these angles, or you can express it in terms of the complex exponentials of these angles. And so let me do it that way. So if I introduce these complex variables on the unit circle, then the equation that is true for any tetrahedron is this equation. All right, so it's more complicated than it looks, because these sums are actually, you're supposed to these are supposed to be symmetric sums where you use the action of S4 on the vertices. So you permute the 1, 2, 3, 4, and you take the sum of all of it, and you also sum over all possible signs. So okay, anyway, so so altogether there's 6 variables, 1 for each edge, 1 for each dihedral angle, and then there are 105 monomials. Actually, there's some mysterious things about this equation that I don't completely understand. It turns out that if you look at all the exponent tuples that appear with a coefficient of -2, so all these exponent tuples and these, and so those are elements of z to the 6th, and it turns out they form a copy of the d6 root lattice. And in fact, the other exponent tuples, they also form orbits under for the Weyl group of d6, and that leads to the fact that this whole expression is actually the character of some virtual representation of the reductive group spin 12. And this is related because, well, although I don't completely understand it, I know it has something to do with there's a hidden symmetry of the moduli space of tetrahedra that was discovered by some physicists in the 1960s, called a Regge symmetry, and it's related to the symmetries that 6J symbols satisfy, if you know what those are. But anyway, it's something in the representation theory. So okay, but anyway, that's sort of an irrelevant remark for our purposes. So but what we want to do is find all the solutions to this equation where the thetas are rational multiples of pi, which means that these z variables, these 6 z variables, should each one should be a root of unity. And so this now is okay. So now this is part of a well-known theory where you're trying to solve a multivariable polynomial equation in roots of unity. And so let me just, I mean, I think probably many of you know about this theory, but let me just say a little bit about, yeah, so what's known about this. So first let me say in more algebraic geometric terms what this is about. So mu will denote the set of all roots of unity of all orders, and we'll be talking about the n-dimensional torus, which is, well, as I said, it's like C star cross C star cross C star n times, and then a subtorus just means in a subgroup of that, an irreducible algebraic subgroup. So it could be, for example, the subgroup where the product of the n coordinates is 1, say. That would be a codimension 1 algebraic subgroup, the subtorus. And then by torsion coset, I mean a sort of a translate of that subtorus by some torsion point. So by some point whose coordinates are roots of unity. So these torsion cosets are of interest because if you look at each of these torsion cosets, it's going to contain lots of points where a lot of torsion points, a lot of points whose coordinates are roots of unity. In fact, they'll be Zariski dense in each of these torsion cosets. And the theorem of all these people is that if you ask for the roots of unity points on any subvariety, then they're all explained by these torsion cosets. So more precisely, if you have any subvariety of C star to the n of this torus, and you ask for all the roots of unity points on that subvariety, satisfying the equations that define X, then they're actually all contained in a finite union of torsion cosets, each of which is contained in X. So there's a very nice structure theorem, and yeah, so it's proved by all these people, and in the one-dimensional case, and then the general case was done by Laurent. And not only is this a theoretical, I mean, not only is there this a sort of theoretical result, but I mean, there's also effective versions of it where you can actually find, I mean, in principle, given the equations of X, you can actually find these torsion cosets. And so that means you can actually write down all these roots of unity solutions in terms of finally many parameterized families, and maybe some isolated points as well. And a lot of people have worked on this too. So not only, I mean, effective, meaning that you can, yeah, there's an algorithm, yeah, and then there's explicit versions that give you bounds and how many solutions and how many of these torsion cosets are, and their algorithms. A lot of people have worked on it. I'm probably forgetting some people. Probably there's some people in the audience right now that I'm forgetting to list here. But anyway, it's, yeah, and even more people have used solutions to this thing to solve various problems in geometry. Maybe I'll say a little bit about how some of these methods work, how you actually can do this, find these solutions. So let me first talk about the approach by Sarah and Tate that was developed further by these people. But let me just talk about a simplified case, just so I don't have to get into all the details. So suppose you just have a single polynomial equation in two variables, and you want to know, yeah, with rational coefficients, and you want to know all the solutions to this, where X and Y are both roots of unity. And to make it even simpler, let me assume that the roots of unity are required to be of odd order. So, okay, so like a cube root of unity and a fifth root of unity. So here's the point. So if you have a solution to this, you can apply a Galois automorphism that will send every root of unity of odd order to its square. And because f has rational coefficients, if you apply that automorphism, that Galois automorphism to this equation, you'll get another equation that says that f of x squared comma y squared is also 0. And so that means, and so now if you want to find those solutions, then now any such solution x, y must satisfy both of these equations. So now you have two polynomial equations and two variables, and so you can solve them simultaneously. You can intersect those two curves, and then that will give you well, that'll give you an upper bound for the solutions, and then you can just, well, you can, I mean, there might be some common components in these two curves, in which case that's where the parameterized families would come from. But anyway, so that this lets you reduce the problem, reduce the dimension, or maybe even find all of the solutions. And there's a variant that works if you're looking at even order roots of unity as well. And you can also, and the same idea, it just works in higher dimensions too. You just have to use an induction on the ambient dimension. So each time you do an intersection, you reduce to a lower dimensional subvariety, or maybe several. And this method works pretty well in practice as well. It works very easily if you're just if you just have a 2-variable problem like this. And for 3 variables, it sort of barely works using a computer. And then for 4 variables, it's usually impractical to do this. And unfortunately, we need to do this for a 6-variable polynomial. There's another approach to this, to looking at solving these kind of equations, and that's just to treat the equation just as a sum of monomials. And each monomial is just a product of powers of powers of roots of unity. So each monomial represents a root of unity. And so what you could try to do is classify all the ways that some number of roots of unity can sum to 0. Like, what are all the ways that 12 roots of unity can sum to 0? And well, that you can do as well. And the reason you can do that is because we know exactly what the relations are between roots of unity. Essentially, all the rational linear combinations of roots of unity that sum to 0, they all just come from the fact that the pth roots of unity, if you add them all up, you get 0 for any prime p, and then you can rotate that relation, or you can take sums of those, and that's basically where all the roots of unity, all the relations come from. And so then once you know that, it's almost like a problem of, it's almost like a combinatorial problem then, to figure out like which combinations of roots of, say, 12 roots of unity can sum to 0. And so yeah, and this was done for larger and larger values of m. So all these people, so the record right now is, these are known now explicitly up to 21 roots of unity. And unfortunately, that's not quite good enough either, because our equation had 105 monomials. And not only that, but we had integer coefficients on those monomials too. So, okay, so what did we actually do to solve this problem? So here's that equation again. So it has too many variables and too many monomials. So what we noticed is that most of these coefficients are even. So if you reduce the equation mod 2, then when I say mod 2, I mean modulo the ideal generated by 2 in the cyclotomic ring. So I mean, so I'm working now in a ring that's not a field, because the full cyclotomic ring modulo this ideal 2, which is not a prime ideal in this ring. But okay, anyway. So you just, when you reduce it in mod 2, you get a sum of 12 roots of unity being 0, except now it's not 0 in the complex numbers, but 0 in this quotient ring. But the same, we were able to classify the ways in which 12 roots of unity can sum to 0 in this quotient ring. And that doesn't quite solve the problem either, because not all of those, just because you have a solution mod 2 doesn't mean you have a solution to the original equation. But the ways these solutions mod 2, it turned out that they fell into parameterized families, each involving only 3 parameters. And so we could, I mean, there are lots of them too. They're like, I mean, depending on how you count them, there are hundreds of them. But so what we did, we took each of those potential solutions, so the solutions that were solutions mod 2, and now you can put those parameterized families back in, substitute them back into this equation, and now you have a 3-variable, a complicated but only 3 variables problem to solve, and that we could do using the first, going back to the first approach, and we could solve those. Of course, I mean, all this is done by computers. This is not something that would have been that we had any hope of doing by hand. I mean, just the combinatorics of it all, just the sheer number of these families well, it was daunting. Okay, anyway, so that's how, so eventually, yeah, we got all the solutions to this in roots of unity, and therefore we got all those tetrahedra with rational dihedral angles. Okay, sorry, oh yeah, so, I just noticed the chat. I should have mentioned Udi. Oh, that's embarrassing. Okay, so back on the list of people who worked on solving equations in roots of unity. Okay, anyway, sorry, Udi. So, all right, so let me now go back to the larger problem about classifying all the Dane invariant zero tetrahedra, not just the ones that have rational dihedral angles. So recall the equation that we need to solve is this one. So we have a tetrahedron, and these L sub j's represent the six edge lengths, and these thetas are the corresponding dihedral angles along those edges. And we need to find all the tetrahedra for which this sum is zero in this tensor product. So one thing you could try to do is you could try to classify these, you could try to divide the problem, so subdivide the problem according to essentially the number of relations that these angles, the integer relations that these angles satisfy. In other words, you can look at the span, the sort of the Q vector space span of these six angles in R mod Q pi. So as an example, if all the thetas are rational multiples of pi, then they're all zero in here, and so the span is zero dimensional. At the other extreme, if you have, so that case zero, that was what we did with all this roots of unity work, and case 6 is where they're independent, where the thetas are independent and also independent of pi. And in that case, well, if the thetas are independent, then they're part of a basis for this vector space. And so the only way you could have a sum, a tensor product, like a sum of tensors like this being zero, is if all the L sub j's were zero. And of course, that doesn't make any that's not a tetrahedron if all the edges are zero. So there are no solutions in case 6 where this span is 6-dimensional. Okay, well, we've done 2 cases, only 5 more cases to go. All right, so, well, let me say what can you say about these things? Let me talk about case 5. So this is the case where the span of these 6 angles is 5-dimensional modulo pi. So, okay, so in this case, okay, so what does that mean? If they're 5-dimensional, that means that there's one relation between these 6 numbers, these 6 angles. There's one integer relation, or rational, or you can scale it, you can clear denominators, one integer relation. So there's going to be a single relation, a single combination of those, integer combination of those that gives you a multiple of 2 pi, say. And when I say unique, it's unique up to a scalar multiple, of course. You can always double it. Okay, and so now, okay, so that's the setup. And now because that's the only relation that these angles satisfy, the thetas in this tensor are almost independent. And the only way you could have this sum then of tensors being zero is if the L sub j's were also proportional to that relation. And so if there's going to be a solution to this at all in this case 5, that means that the L's, these edge lengths must be proportional to these integers, the integer coefficients that appear in this relation. And well, they're also edge lengths, so they have to be positive. And so, yeah, so up to scalar, you might as well assume that these edge lengths are these A's, and they are these positive integers. And the other observation you can make is that, well, this is just a general property of tetrahedra, that if you know the edge lengths of a tetrahedron, you know the tetrahedron. And so they determine the dihedral angles. And algebraically, the way that manifests itself is by saying that, well, they algebraically determine the cosines of the angles, or if you want, these complex exponentials are determined. So these z sub j's, these complex exponentials of the dihedral angles, each one of them is an explicit algebraic function of the edge lengths. And so now, well, if you take this angle equation and you complex exponentiate it, you get, and remember that the A's are the same as the L's, you get an equation like this. You have this power of these, the product of these powers is 1. And so these Z's are explicit algebraic functions of the edge lengths. In fact, turns out that they all live in a degree 2 extension of the rational function field. They're just degree 2 over Q join L1 through L6. And so the type of the problem that we need to solve in order to handle this case 5 is to find the positive integer solutions to an equation like this. And well, I'm not sure if this falls into, I don't know, what I'm hoping is that somebody in the audience can tell me like, oh, this is like a special case of this kind of problem. Like, I mean, I don't think this doesn't look like Mordell-Lang or anything like that to me. So I was wondering if anybody has seen things like this before, if problems of this type. I mean, even in the case where the Z's are just rational functions of the L's. Yeah, I'm not sure. I mean, so yeah, and yeah, so and some of the undergrads were I mean, you can just try various integers and see if they work. I mean, you can just search for solutions, doing just a brute force search. You can start looping over small integers, L's, and then you can solve for these Z's. They're just algebraic functions of these. They all actually live in some, as I said, they all live in the same quadratic extension. In fact, the extension they live in is the quadratic extension that's generated by the square root of -1 times the volume of the tetrahedron, as it turns out. Okay, anyway, so all right, so that's okay, so that's where this stands. And yeah, but yeah, actually the undergrads, when they did this, they actually did find some solutions to this. And in fact, they found enough that they recognized a family. So they actually discovered a new family of Dane invariant 0 tetrahedra this way, by noticing a pattern in the solutions that they found here. Okay, and this is case 5, and there are also those other cases. So in general, if you have fixed some other dimension of the span, so it's called D. So this is just the analog of what I did on the previous slide. So, but stated maybe slightly different terms. So let me take, okay, so these Z's are the complex exponentials of those angles. And understanding the span of these is like looking at the multiplicative group generated by these complex numbers of absolute value 1. And you can take the smallest algebraic group that contains those. So let's call it H. And so unlike all the algebraic subgroup, there's going to be some subgroup defined over Q. Maybe it's not connected, but anyway, so you get it's like a torus, or maybe it's like a torus cross a finite group or something like that. Okay, and because of the assumption on the dimension of the span, the dimension of this torus is going to be D. It's the same D as here. And if you take its Lie algebra as an algebraic group over Q, so you get a subspace of Q to 6, and then you can take the orthogonal complement, which is sort of keeping track of the relations, or if you want, it's keeping track of the monomials that cut out this subgroup H. It's keeping track, in other words, it's keeping track of the multiplicative relations among the Z's, or if you want the integer relation among the thetas. So that's some subspace. And if you take the P of that subspace, so that's going to be some projective linear subspace of inside P5. Yeah, so it's just some lower dimensional projective space. And then in these terms, in these algebraic geometry terms, this Dane invariant 0 condition, to say that this tensor is 0, it amounts to saying that this point, which a priori is a point of P5 cross GM to the 6th, this condition says that it lies in this product of varieties. So the L vector, the L point has to be in this line, these relations. and then the H, and then, well, the Z's are, well, by definition, they're in this H. And this subvariety, it's you can figure out what its dimension is, because I mean, H is d-dimensional. And so the Lie algebra of H is d-dimensional, and this will be 6 minus d, and then this will be 5 minus d. And so, yeah, so you get 5 minus d plus d, and so it's 5-dimensional. On the other hand, so you have that equation, you have this, I mean, this some equations. On the other hand, you have the relations that tell you that well, as I said, the edge lengths determine the dihedral angles, and that amounts to saying that the edge lengths and these complex exponentials of the dihedral angles, they satisfy various polynomial conditions, and those polynomial conditions define some other variety to them that's independent of the tetrahedron. It's just some variety that tells you what the relations are between those things, and that is also 5-dimensional. Some 5-dimensional. It's as I said before, the moduli space of similarity classes of tetrahedra is a 5-dimensional space. So that's some other 5-dimensional space inside here. And now we're looking for points that lie on both of these. So we're intersecting a 5-dimensional variety and another 5-dimensional variety inside an 11-dimensional variety, this one. And so you expect them not to intersect at all. And so this, I mean, the expected dimension of the intersection is -1. So it's an unlikely intersection. But of course, so for any given H, you can actually compute this in principle, but there are countably many algebraic subgroups to try. So it's some kind of unlikely intersection problem. So where you might, and sometimes you do get, as we said, we know there are some infinite families in here. So sometimes this dimension is larger than we expect. Okay, so that's what I know about that's some. Well, it's some kind of problem. I don't know. So so Udi, I wish I could say more about. I wish I could say I could solve this problem and say, oh, here's this beautiful result. I've classified all these things, but but right now I don't even know what framework this belongs to. Is whether this, and so so I think I'll end here. Maybe I'll just leave you with this picture of what we know about the problem so far of these examples. So so thank you very much, and and happy birthday, Udi.
Thanks.
Well, thanks a lot. Just that there are going to be plenty of questions, and I'll let others raise those first.
What did you say?
It's time for questions. If you'd like to ask a question, go ahead.
Yeah, really beautiful talk. And of course, it's always nicer when there's still it's a mystery behind it with all these connections. So I have no idea. First of all, I don't think I really worked on that exactly, even though I brushed by. This LH intersect